Welcome to Science to Sleep By. Tonight, we drift through the quiet reaches of the solar system, where a mysterious visitor may not be leaving at all. Astrophysicist Avi Loeb, known for his daring ideas that challenge the boundaries of mainstream science, has turned his gaze toward a rare interstellar traveler 3I Atlas, the third interstellar object ever detected passing through our cosmic neighborhood. But what if this one, unlike the others, has decided to stay? As we close our eyes and let the stars unfold, we'll explore the science, the mystery, and the possibilities behind this lingering cosmic guest, one that might be rewriting what we know about interstellar travel and our own celestial home. It began, as many discoveries do, with the faint glimmer of data, a subtle shift of light against the black canvas of space. The Pan-STARRS Observatory in Hawaii, its sensitive eyes always watching the night, noticed something unusual in the outer reaches of our solar system. A new point of light, moving not quite like the others, tracing a path that defied the quiet order of our familiar planets and asteroids. They called it 3 Atlas, the third interstellar object ever found, after the strange wanderer Oumuamua and the comet 2I Borisov. But unlike its predecessors, this one carried a mystery unlike any before it. Its motion suggested something extraordinary. It might not be passing through. It might be staying. In the soft glow of midnight observatories, astronomers adjusted their telescopes and recalibrated their minds. When you live in the cosmic quiet, every new point of light is a whisper from the unknown. Atlas, they soon realized, was not born of our sun. Its velocity, its trajectory, and its orbital inclination all told a different story. This was an interstellar visitor, an object forged beneath another star's light, sculpted by the gravity of another system, and now wandering among ours. Yet, unlike Oumuamua, which darted through the solar system with the restless haste of a traveler on a one-way journey, Atlas seemed to slow, to linger, as if caught in the gravity of our home. To appreciate what that means, imagine the vast emptiness between stars, the cold, soundless dark, where gravity is weak and time stretches long. Across those spaces drift countless fragments of creation, shards of rock, ice, and dust, ejected from the birthplaces of alien worlds. Occasionally, one of them slips close enough to another star's gravity well, and for a fleeting moment, it becomes visible to someone watching. That is how Oumuamua first appeared in 2017, streaking across the sky at 315,000 kilometers per hour, tumbling end over end, escaping our sun's pull as easily as a stone skipping across a pond. It came, it astonished, and it was gone. Then in 2019 came 2 Borisov, a comet-like traveler rich in cyanide and carbon, more familiar in its composition, but still unmistakably foreign in its origin. These were cosmic postcards, brief, brilliant, and gone before we could ask them who sent them. But 3 Atlas changed that rhythm. Detected in 2022, its path didn't behave the way an interstellar objects should. Instead of slicing cleanly through the solar system and vanishing into the void, it seemed to curve more gently, almost tenderly, around the sun. Its speed was lower than expected, its arc more subdued. Calculations showed something remarkable. The sun's gravity had taken hold of it. For the first time in recorded history, an interstellar object might have been captured, held within our solar system's grasp, bound to orbit our star like one of its own. In the stillness of late-night discussions, astronomers and astrophysicists began to whisper the implications. If Atlas had truly been captured, it would mean that our solar system has grown not in physical size, but in story, in complexity, in the quiet drama of celestial mechanics. Our sun would have adopted a foreign child, a fragment from another world, now circling beneath its light. Avi Loeb, ever the questioner of cosmic conventions, looked at this event not merely as an anomaly, but as an opportunity. In his view, each interstellar visitor carries with it the potential to reshape how we see the universe, not as a closed system of separate stars, but as a vast ocean of connected worlds, where matter drifts freely between suns. If 3I Atlas truly stays, it would stand as the first evidence that our solar system is not isolated, that across millions of years, it can collect fragments of other systems' cosmic seeds traveling between the stars. The orbit of Atlas tells a story of delicate capture, a dance between speed and gravity. When an interstellar object enters a solar system, it typically moves too fast to be held. The sun's pull accelerates it briefly, but the object escapes, flung back into the galactic tide. For capture to occur, something must slow it down, perhaps a gravitational interaction with Jupiter, the solar system's massive gatekeeper, or with another large body that saps just enough momentum to trap it. That is one theory behind Atlas's curious behavior. As it passed through the outer planet's domain, perhaps Jupiter's gravity reached out like a gentle hand, altering its path and reducing its velocity just enough for the sun to hold it in orbit. If that is true, then Atlas's arrival marks a rare cosmic event, one that could last for millions of years. Imagine it now, somewhere in the distant reaches beyond the orbit of Saturn, drifting slowly along a looping path around our star. It is small, perhaps only a few hundred meters wide, its surface darkened by radiation and cosmic dust. Sunlight touches it faintly, glinting off icy minerals and rocky scars. It moves silently, watched by no one but the patient eyes of observatories and the minds of those who dream beyond the Earth. There is a strange comfort in the thought that something from another system has decided to stay. It is as if the vast emptiness between stars has sent us a quiet companion, a reminder that we are not alone in the galaxy's drift. For the United States night sky watchers, who have long looked upward with telescopes and wonder, this story carries the same spark that once sent rockets to the moon. It is discovery not through motion, but through reflection, the understanding that our solar system is not a closed chapter, but an open page in a larger galactic story. Even now, scientists are refining models, running simulations, testing how such an object could remain. The equations are delicate, the probabilities small, but the evidence remains enticing. Some trajectories show Atlas looping through the outer solar system for centuries. Others predict a slow inward drift before settling into a long, eccentric orbit. Whatever the outcome, the mere possibility expands our view of the cosmos, not as a static system, but as a living network of wandering objects and chance encounters. Every so often, our telescopes catch faint traces of these visitors, a spectral line here, a reflected glimmer there, and through them, we sense the vastness of what lies beyond. They are emissaries of distant suns, fragments of unknown histories. And in 3i Atlas, for the first time, we may have found one that has chosen to linger. Its presence reminds us that the borders of the solar system are porous, that gravity can weave together the stories of worlds separated by light years, and that even across the emptiness of interstellar space, connections can form. In that quiet truth lies the essence of cosmic wonder, that something born beneath another star's light now circles our own, caught in an eternal, graceful drift through the same sunlight that warms our world. The data shows it, the equations predict it, and the human heart, ever drawn to the infinite, feels it when the scientific world encounters something unfamiliar. It often responds first with caution, then with curiosity. But for Avi Loeb, that order is reversed. His instinct, almost always, is to question before conforming, to ask, what if, before saying, impossible. In the story of 3i Atlas, this instinct once again becomes central. While many astronomers were content to catalog Atlas as another interstellar oddity, Loeb looked deeper, not only into the data, but into the assumptions that shape how we interpret it. His work has always walked the fine line between the empirical and the imaginative, balancing rigorous physics with a childlike wonder that refuses to be silenced by convention. To understand why Avi Loeb's voice matters in the discussion about 3i Atlas, one must first understand his journey through science. Born in Israel, Loeb grew from a young scholar of theoretical physics into one of the most visible and sometimes controversial astrophysicists of our time. He led Harvard's astronomy department, advised NASA, and published hundreds of papers on black holes, cosmic dawn, and interstellar exploration. Yet it is not his credentials that make him stand apart. It is his courage to confront the boundaries of acceptable thought. In a field that often values consensus, Loeb has chosen curiosity. When Oumuamua passed through the solar system in 2017, its strange acceleration puzzled astronomers. Some attributed it to natural causes, outgassing, radiation pressure, or simply measurement error. Loeb saw in it a question too big to ignore. Could it have been something artificial? Perhaps a fragment of alien technology? He wrote a paper proposing that possibility, not as a conclusion, but as a hypothesis that deserved to be considered. The reaction from the scientific community was swift, divided, and at times, dismissive. Yet Loeb remained calm. To him, science was not about comfort. It was about exploration, and exploration required the bravery to ask questions that made others uneasy. Now, with 3I Atlas, Loeb finds himself once more at the intersection of data and imagination. The object's apparent capture by the Sun, its slow, steady orbit, and its interstellar origin raise questions that sit at the edge of known physics. Could such a thing happen naturally? Could an interstellar object lose just enough energy to remain bound? Yes, perhaps. But Loeb sees another layer to the mystery. He sees the possibility that Atlas, like Oumuamua, might be part of a broader cosmic pattern, evidence of movement, communication, or intentional design in the fabric of the galaxy. Loeb's perspective is not about believing in aliens. It is about not ruling them out. In his view, the universe is too vast, ancient, and too full of potential for us to assume we are alone. The galaxy, he says, may already be full of relics, not necessarily active spacecraft, but ancient technologies, debris, or probes that once served civilizations long gone. If even a fraction of the stars in our galaxy hosted intelligent life at some point, the night sky could be littered with the remnants of their journeys. In that light, every interstellar visitor becomes a messenger from the past, carrying hints of what others might have achieved before us. To the U.S. audience, accustomed to the legacy of exploration and bold inquiry, Loeb's mindset resonates deeply. He embodies the same spirit that once guided NASA's early pioneers, the refusal to accept limits on imagination. When he speaks about interstellar objects, his voice is steady, precise, but filled with quiet conviction. He reminds his listeners that science grows not by repeating what is known, but by challenging what is assumed. For Loeb, the most dangerous phrase in science is not, "I don't know," but "that's impossible." The discussion around 3I Atlas exemplifies that philosophy perfectly. Most scientists agree that its capture is rare, perhaps even unprecedented. Yet for Loeb, rarity is not reason for dismissal. It is a signpost for investigation. He imagines scenarios where objects like Atlas could be more common than we think, where interstellar material is constantly exchanged between systems, creating a dynamic galactic ecosystem. Perhaps our Sun has collected many such visitors over billions of years, each now orbiting silently beyond Neptune, blending into the background of comets and icy bodies we have yet to study. In his recent talks and writings, Loeb has emphasized that we must learn to see differently. Our instruments are improving. Telescopes like the Vera Rubin Observatory and missions like the James Webb Space Telescope can now detect the faintest signatures of movement, composition, and light. With that clarity comes responsibility. If something strange appears in our data, we cannot dismiss it simply because it doesn't fit into our current models. Science, he says, must remain humble before the unknown. That humility, paradoxically, requires boldness, the willingness to ask questions without fear of ridicule. Loeb's philosophy reaches beyond science and touches the human experience of wonder. He often compares the universe to an ocean, vast and deep, with most of its treasures still hidden beneath the surface. The discovery of 3I Atlas is, in his view, like finding an unfamiliar shell on the shore. You could toss it aside, assuming it's just another rock, or you could pick it up, examine its patterns, and realize it may have come from a distant reef, carried across currents we barely understand. In that metaphor lies his entire approach to cosmic discovery, the belief that every anomaly deserves attention, that curiosity is not a weakness, but a compass. For Loeb, the story of 3I Atlas is also a story about time. Interstellar objects are ancient. They were formed when their parent systems were young, ejected by gravitational interactions, and sent drifting through the galaxy for millions or billions of years. When one arrives here, we are not just observing an object. We are peering into a fragment of galactic history. Its chemistry, its orbit, even its texture are records of processes that occurred long before Earth's first multicellular life began to evolve. Loeb's fascination lies in decoding those stories, understanding not just where these visitors come from, but what they represent in the grand narrative of cosmic evolution. Critics sometimes accuse Loeb of stretching beyond the data, of entertaining ideas that belong more to science fiction than science. Yet he sees that criticism as evidence of a deeper problem that modern academia can sometimes grow too narrow. The history of astronomy, he reminds us, is filled with moments when accepted truth was overturned by a single observation that refused to fit. Once, the idea of galaxies beyond our own was dismissed. Once, black holes were theoretical curiosities, not cosmic realities. Once, the notion that planets orbited other stars was speculative at best. Today, all those once radical ideas are part of accepted fact. What, Loeb asks, will tomorrow's truth look like? In the quiet rhythm of his thinking, there is something deeply human. The same restlessness that drove early astronomers to map the heavens by candlelight. That sent Voyager probes beyond the planets. That built radio dishes to listen for whispers from the stars. Loeb stands in that lineage, not as a rebel against science, but as one of its most faithful practitioners, faithful to its original promise to never stop asking. In the tale of Three-Eye Atlas, he finds both a mystery and a mirror, a chance to reflect on how we confront the unknown, and whether we dare to imagine that the universe might be more alive, more interconnected, than we ever believed. As the world's telescopes turn toward the edges of the solar system, searching for faint glimmers of this lingering traveler, Loeb's words echo through observatories and lecture halls alike. The universe is not waiting for our permission to surprise us. In that simple statement lies his message to the world that discovery demands both skepticism and wonder, that data and imagination are not enemies, but allies, and that sometimes the only way to understand the cosmos is to question the ordinary in the grand cosmic ballet. Every object follows a rhythm set by gravity's unyielding hand. Comets streak inward from the cold Oort cloud, curve around the sun in long ellipses, and retreat once more to the frozen edge. Asteroids circle steadily in belts of rock and metal, while planets trace paths of perfect balance between motion and pull. Yet among these predictable patterns, one object now dances to a rhythm that defies expectation: Three-Eye Atlas, the third known interstellar visitor, whose orbit seems to break the rules written by the stars. In the quiet calculations of astronomers, this object should have come and gone, passing briefly through our solar system like Oumuamua and 2I Borisov before it. But Three-Eye Atlas is not leaving. Its trajectory has curved too tightly, its speed has fallen to low, and against all statistical odds, it seems to have surrendered itself to the sun's gravity. At first, the numbers didn't make sense. When an interstellar object approaches our solar system, it is almost always traveling at extraordinary velocity. To escape the pull of its parent star and traverse the void between systems, it must be moving faster than the local escape velocity, typically tens of kilometers per second. By the time such an object reaches our sun, its speed should have increased even more, accelerated by the gravitational attraction of the solar system's center. For Oumuamua, that speed was about 87 kilometers per second. For 2I Borisov, around 33. These are cosmic sprints fast enough to ensure that no amount of solar pull could trap them. Once their journey past the sun was complete, they continued outward forever, destined never to return. Three-Eye Atlas, however, told a quieter story. When astronomers plotted its path, they noticed something unusual: its hyperbolic excess velocity, the measure of how fast it was moving when far from the sun's influence, was unexpectedly low. Instead of racing through space, Atlas seemed to be drifting, almost meandering, with a relative speed of less than 1 kilometer per second compared to the sun's frame of reference. In cosmic terms, that is almost stillness. Such slowness suggested something remarkable. When it entered our solar system, its speed was only barely enough to qualify as interstellar. The line between bound and unbound, between visitor and resident, is razor thin, and Atlas appeared to balance right on it. When astronomers integrated its trajectory backward through time, tracing its path from where it might have come, they found that it did not point cleanly to the galactic plane or any known stellar system. Instead, its inbound vector appeared random, suggesting it was not ejected recently from any specific star. That randomness itself was part of the mystery, as though Atlas had been wandering the interstellar medium for millions of years, losing energy through tiny interactions with dust, gas, and perhaps even other gravitational fields, until it drifted so slowly that our sun could finally catch it. In a universe ruled by momentum and mass, such capture events are vanishingly rare. Gravity, in its simplicity, follows precise rules. To be captured, an object must lose energy, it must give up a portion of its speed to something else. In most solar systems, that something is a planet. Jupiter, with its enormous mass, often acts as a celestial gatekeeper, deflecting asteroids and comets or pulling them into new paths. If 3I Atlas passed close enough to Jupiter or Saturn during its entry, it could have lost just enough kinetic energy for its hyperbolic trajectory to transform into an elliptical one. That would mean, for the first time in human observation, an interstellar body has become gravitationally bound, a permanent resident in our solar system. Simulations run by orbital dynamicists have tested this idea. They show that under the right conditions, a slow-moving interstellar object could indeed be captured through multi-body interactions where the combined gravitational influence of the Sun and one or more giant planets reshapes its orbit. Such interactions can drain away just enough velocity to transform an open-ended escape curve into a looping, solar-centered ellipse. If that is what happened with Atlas, it would be one of the most extraordinary natural captures ever recorded. Its current trajectory appears slightly eccentric, but closed, meaning that it will not escape the sun's pull, at least not for millions of years. This revelation ripples through astronomy in profound ways. It challenges the long-held assumption that interstellar visitors are fleeting phenomena, too fast and too rare to be caught. If our solar system can capture one, then perhaps it has done so before. There could already be dozens, perhaps hundreds of such captured interstellar objects orbiting quietly among the distant icy bodies beyond Neptune, indistinguishable from native comets until we look closely enough. The idea turns our solar system from a self-contained family into a cosmic crossroads, where objects from other stars may come to rest. For observers and dreamers alike, the idea of Atlas staying carries a poetic resonance. Picture it now. A dark, irregular fragment of rock and ice, tumbling slowly in the dim sunlight near the outer planets. Its surface has been battered by cosmic rays for eons, etched with the scars of deep time. No atmosphere, no light of its own, just a silent, ancient traveler, now held within the invisible threads of the sun's gravity. The starlight it once reflected from another system now glimmers faintly across our telescopes. Its journey, once endless, has become an orbit, a return, a home of sorts. But in the quiet of that orbit lies a deeper question. Why did it slow enough to stay? The physics of capture require a delicate balance, and though the Jupiter assist hypothesis fits, some researchers wonder if there might be other explanations. Perhaps Atlas passed through a dense region of interplanetary dust, experiencing minute drag forces that slightly reduced its speed. Or perhaps it collided with another small body, a rare but not impossible event in the crowded outer reaches. Even a tiny impact could have dissipated enough energy to alter its fate. Some speculate about non-gravitational forces, like outgassing jets or sublimation effects, though so far, Atlas has shown little evidence of cometary activity. Its silence makes the mystery deeper. Avi Loeb's interest in this behavior stems precisely from this silence. In the language of orbital mechanics, every motion has a cause. For Atlas to remain means that something unseen acted upon it, or that its initial conditions were uniquely poised for capture. Either scenario pushes the boundaries of our models. Loeb's approach is to treat such anomalies not as errors, but as opportunities, moments when nature gives us a clue that our understanding is incomplete. If Atlas's orbit is stable, then we may be witnessing a rare event in the cosmic record, the blending of interstellar and solar origins into one continuous system. The implications stretch far beyond academic fascination. If 3I Atlas is bound, it becomes a prime target for future missions. Imagine a spacecraft sent to study it up close to sample its material, measure its isotopic ratios, and determine whether it truly comes from another star. Such a mission could reveal more about the chemistry and physics of distant systems than decades of remote observation. For scientists, this object is not just a curiosity. It is a time capsule, preserving the molecular fingerprints of another world. For dreamers, it is something more, a symbol that the galaxy is not divided, but connected, that our sun and the stars beyond are part of a shared celestial conversation, and in the language of motion and light. The orbit of 3I Atlas reminds us that even in the vast stillness of space, nothing is permanent. What was once free can become bound. What was once foreign can become familiar. Each calculation, each telescope image, deepens our sense of how delicately balanced the universe is. The very forces that hold planets in their paths can also capture travelers from afar, turning wanderers into companions. Somewhere in that realization lies a quiet comfort, the understanding that in the endless motion of the cosmos, even the most distant stranger can find a place to stay. Before 3I Atlas found its place within our solar system, it lived a life adrift in the vast, silent reaches between the stars. Its journey began long before our species could name the constellations, before Earth had grown its forests or oceans, perhaps even before the sun itself had ignited into light. To trace the origins of Atlas is to move backward through cosmic time, to follow a single fragment of matter through billions of years and unthinkable distances, across a galaxy that has always been in motion. Every object carries a history written in its composition and orbit. And though Atlas is only a speck of dust compared to the immensity of space, it is a survivor of another world, a messenger from a system that once lived and breathed under a different sun. The question of where it came from is both scientific and philosophical. Astronomers can model trajectories, simulate gravitational paths, and estimate galactic motions, but the truth of its birthplace may forever remain hidden beyond the limits of observation. Still, science offers possibilities, each one a story of creation, destruction, and cosmic exile. One possibility is that 3I Atlas was born in the turbulent disk of a young star, much like our sun once was. In such disks, dust and gas swirl in chaotic motion, colliding, merging, and forming the first solid bodies, planetesimals. Over millions of years, these bodies grow into planets, moons, and asteroids. But not all find stable homes. Gravitational encounters can fling smaller bodies outward at immense speeds, ejecting them from their birth systems and sending them wandering through interstellar space. Atlas may be one of these outcasts, a remnant of some ancient planetary nursery, expelled by the violence of formation and left to drift in the dark. If so, its story is shared by countless others. Our own solar system likely expelled trillions of similar fragments during its youth, scattering them into the galactic sea. Each star, in its turn, contributes to this migration, filling the Milky Way with debris. Silent travelers between worlds. Some of these objects might carry within them the chemical fingerprints of their origins, isotopic ratios that tell of temperatures, pressures, and elements that once surrounded another star. To study Atlas is to hold a small piece of another solar system in our hands. To touch material that once felt the gravity and radiation of a different sun entirely. Another possibility is that Atlas emerged from a system older and more chaotic than our own, perhaps from a binary star pair, where gravitational forces tug and twist continuously, or from a system disrupted by a passing giant. When two stars orbit close together, their combined gravity can sling small bodies outward like stones from a sling. Over time, millions of such objects can be ejected, forming vast clouds of interstellar material. If Atlas came from such a place, its trajectory through space may have been shaped by gravitational turbulence, its velocity altered by stellar encounters until it slowed enough to wander near our sun. Each tug, each acceleration, each subtle deflection would have carved part of the path that brought it here. It's also possible that 3I Atlas comes from a system already gone, a solar family extinguished long ago. Across the Milky Way, stars live and die in cycles. Some swell into red giants, shedding layers of gas and dust before fading into white dwarfs. Others die violently, collapsing in supernova that scatter their planets and asteroids into the void. Atlas might be a survivor of such an event, a fragment that escaped the gravitational chaos of a dying star, launched outward by a final explosion, carrying within it the remnants of a world that no longer exists. If we could touch its surface, we might find isotopes or minerals forged in those cataclysmic fires, the ashes of a sun that burned its last long before ours began to shine. The age of 3I Atlas, if we could measure it precisely, would tell us much. Interstellar radiation bombards unprotected surfaces with high-energy particles that darken and weather them over time. The more cosmic rays a body has absorbed, the longer it has wandered the interstellar void. Its surface chemistry might reveal a record of billions of years of exposure, a cosmic diary written in molecular scars. By comparing these patterns with those of known comets and asteroids, scientists could estimate how long Atlas has been away from any star. It may have left its home before Earth itself was formed, drifting through a galaxy still young, a galactic orphan on a path dictated only by momentum and chance. The physical composition of Atlas adds to the mystery. Initial observations suggest a faint, inactive surface not glowing with the tail of a comet, not rich in sublimating ice, but quiet and dark. This implies that its materials are stable, perhaps rocky, perhaps coated in carbonaceous compounds hardened by radiation. In this, it resembles Oumuamua, which also showed no clear signs of typical cometary activity. Such stability could mean that Atlas originated in the inner regions of its home system, closer to its star, where heat drove away volatile ices and left behind dense, mineral-rich rock. If so, it may once have been part of a larger body, a moon, a planetesimal, or the fragment of a world shattered by collision. Over time, gravitational chaos or impact forces could have sent it hurtling outward, away from the warmth of its birth star, and into eternal exile. But there's another, more speculative idea, one that Avi Loeb himself finds worth contemplating. What if 3I Atlas was not formed naturally? What if its smooth trajectory, its peculiar velocity, and its resilience are not coincidental, but intentional? Loeb has often argued that humanity should not shy away from considering the artificial. In his view, interstellar objects could represent relics of technological civilizations, derelict spacecraft, fragments of long-lost machines, or even exploratory probes designed to drift silently between systems. The odds of encountering such an artifact are low, but not zero, and in a galaxy of hundreds of billions of stars, even rare events become inevitable. If 3I Atlas were such a relic, it would mean that we are not the only architects of matter in motion, that other intelligences have once sent their creations into the same cosmic currents we now study. Even if that idea remains speculative, it serves a purpose. It forces us to look at Atlas not just as an object, but as a story and narrative of motion that began somewhere far away and continues now within our own celestial neighborhood. Each interstellar visitor carries a kind of message, not in words or symbols, but in presence alone, proof that matter travels freely between stars, that the galaxy is not a set of isolated islands, but an interconnected sea. The very existence of Atlas speaks to the unity of creation, the way stars and their planets exchange fragments, trading atoms across light years, weaving a galactic ecosystem that links distant suns in invisible bonds. To imagine its birthplace is to imagine a system much like ours, orbiting a star that rose and set on alien worlds. Perhaps that star still burns, pale and distant, unaware that one of its children now circles another sun. Or perhaps it has long since gone cold, its planet stripped away, its memory preserved only in this wandering fragment. Somewhere in the Milky Way, the light of that original home still travels outward, though it may never reach us. Atlas, in its quiet motion, carries that light's echo, a piece of history moving through the present. If the captured orbit of 3I Atlas is confirmed, then its journey has reached a kind of conclusion. It has traveled across the galaxy, crossed the gravitational boundaries of countless stars, and now it circles ours, a long arc of motion drawn to a pause. Yet this is not the end of its story, only another transformation. The sun's gravity holds it now, but time moves endlessly, and even captured objects eventually change course. For now, though, Atlas remains, whispering through the outer dark, its every orbit a reminder that the universe is not static, but alive with movement, that what once belonged to another star now belongs, if only for a while, to use. A very object that drifts through the void carries within it a secret, a record of its birth, its travels, and the conditions that shaped it. For astronomers, 3I Atlas is not only a mystery of motion but of material. Its orbit tells a story of capture, but its surface tells a story of origin. To understand what this interstellar visitor truly is, scientists must look beyond its path and into its composition, into the quiet chemistry and structure that define it. What lies beneath its dark shell could reveal not only where it came from, but also how worlds form across the galaxy, and how matter remembers the suns it once circled. When 3I Atlas was first detected, its faintness stood out. It reflected little light, making it difficult to observe in detail. Unlike the bright comets that blaze tails of gas and dust as they near the sun, Atlas appeared subdued, silent, unresponsive to solar warmth. This absence of outgassing was the first clue that it might differ from typical comets or icy bodies. In astronomy, the behavior of an object near the sun is often a fingerprint of its makeup. Comets, filled with volatile ices, water, methane, carbon dioxide, awaken when heated, venting material into long luminous trails. Asteroids, by contrast, remain inert, composed mostly of silicates and metals. 3I Atlas showed none of the activity expected of an ice-rich traveler, suggesting that it is made of tougher, less volatile material, something rocky, carbonaceous, or coated in a radiation-darkened crust. Spectral analysis, the study of light reflected from an object's surface, is one of the few tools astronomers can use to decode such mysteries from afar. By splitting its light into wavelengths, they can identify the chemical bonds that absorb or reflect certain colors. For 3I Atlas, early data revealed a reddish hue, similar to many outer solar system objects, a tone often caused by organic molecules known as tholins. These complex hydrocarbons form when radiation interacts with simpler compounds like methane or ammonia, creating a residue that darkens and reddens over time. Tholins are found on Pluto, on Titan, and on many Kuiper Belt objects, hinting that Atlas's surface has been exposed to cosmic radiation for millions, perhaps billions, of years. Its color is not just pigment. It is history, a surface aged by starlight and cosmic rays, a quiet testimony to its ancient journey. Yet, even if its exterior is hardened and dark, the interior may be something else entirely. Interstellar objects often have layered compositions, like time capsules sealed within stone. Beneath Atlas's surface crust could lie ices preserved from its formation, locked away from sunlight for eons. If that is true, then inside this silent traveler may exist pristine material older than our solar system, frozen remnants of a world that never was. Scientists dream of what such samples could tell us. The isotopic ratios of hydrogen, carbon, and oxygen could reveal the temperature and pressure of its birthplace. The mineralogy could tell whether it formed near a star or in the cold reaches beyond a system's frost line. Even a trace of organic molecules would deepen our understanding of how the ingredients of life scatter through the galaxy. Some researchers speculate that 3I Atlas may resemble a fragment of a larger body, perhaps the broken shard of a planetesimal, one of the building blocks from which planets are born. In the early days of a solar system, these rocky bodies collide violently, merging or shattering in endless cycles of destruction and creation. If Atlas was once part of such a collision, its composition might preserve clues to the chemistry of an entire star system. Certain elements, magnesium, silicon, iron, would tell us it formed close to its star. Volatile rich compounds, water ice, methane, ammonia would suggest a birth in the colder outer regions. Each molecule would be a clue, a sentence in the story of another sun's creation. The darkness of Atlas's surface could also mean it has spent unthinkable ages drifting between stars, weathered by radiation into something chemically transformed. In the void of interstellar space, high-energy particles constantly strike exposed material, breaking molecular bonds and forging new ones. Over millions of years, this process can alter the chemical structure of an object's surface, turning reflective minerals into inert, carbon-rich films. The result is a blackened crust that absorbs most of the light that touches it, hiding the brighter interior beneath. This may explain why Atlas appears so faint even to powerful telescopes. It is a relic wrapped in its own history, its surface scarred by the endless bombardment of cosmic rays. Avi Loeb and other astrophysicists view this as a precious opportunity. An interstellar object, especially one that seems bound to the solar system, is a laboratory of galactic chemistry. It holds within it material untainted by the sun's radiation or the processes that shaped our own planets. Studying it would be like opening a time capsule from a different corner of the Milky Way. If a future mission could visit Atlas as missions like OSIRIS-REx did with the asteroid Bennu, we could compare its isotopic ratios with those of known solar system bodies. A mismatch would confirm its alien origin beyond all doubt. Such data could refine models of how elements are distributed across the galaxy, how planetary systems share matter, and how the seeds of worlds, perhaps even life, migrate from one star to another. The idea that interstellar objects might carry organic compounds fascinates scientists and dreamers alike. Carbon-based molecules are common in the universe, forming easily in the cold molecular clouds where stars are born. Many of these compounds, when shielded within solid bodies like Atlas, can survive cosmic radiation for billions of years. If some of these molecules resemble amino acids or prebiotic chemicals, they could support the theory of panspermia, the idea that the building blocks of life can travel through space, seeding worlds as they go. Atlas could, in this sense, be a messenger not just of matter, but of possibility. It could carry the same ingredients that once fell onto a young Earth, sparking the chemistry that led to life. Of course, these ideas remain speculative until direct evidence is gathered. But that is precisely what makes Atlas so compelling. It invites us to imagine a chain of connection stretching across the galaxy, a vast exchange of dust, ice, and organic material flowing between systems. Each interstellar object we find adds another link, another thread in that invisible network of galactic recycling. The universe, it seems, does not waste its creations. What one star casts away, another may someday receive. Atlas is part of that cycle, a traveler carrying within it atoms that once belonged to a distant world and will, in time, become part of ours through the shared gravity of the sun. Even its density and shape hold clues. Some models suggest that 3I Atlas might be elongated, spinning slowly as it moves, perhaps fractured by ancient impacts. Others think it could be irregular, a cluster of smaller fragments loosely bound by gravity. Its rotation rate could tell us whether it is monolithic or rubble-like. A dense, solid body would imply a rocky composition. A porous, fragile one would suggest a mixture of dust and ice. Each possibility tells a different story about its past, about the violence or tranquility of its home system, about how it survived ejection into the void. The more astronomers study 3I Atlas, the more they realize that its physical nature is a map of cosmic history. It is a fossil, not of life, but of formation, a record of how matter organizes itself under the laws of physics, wherever gravity and time exist. To touch it, to hold even a grain of its dust, would be to hold a fragment of another world, a physical link to the vast processes that bind the galaxy together. It reminds us that the elements we study here, carbon, iron, silicon, oxygen, are not uniquely ours. They are shared ingredients, shaped by countless stars, scattered across space, and reunited in endless cycles of creation. And so 3I Atlas drifts on, its surface dark and ancient, its interior cold and silent. Somewhere within that frozen stillness lies the memory of another sun's light, the chemical echo of a world that may have vanished long ago. Every wavelength of light that bounces off it carries a whisper of that distant past, traveling across millions of miles to reach our telescopes and our minds. To understand what it's made of is to understand a fragment of the galaxy itself, to glimpse the unity of matter that connects all stars, all planets, all worlds in the ever-expanding tapestry of cosmic investigation. Few figures have stirred as much curiosity, debate, and daring speculation as Avi Loeb, known for challenging conventional astrophysics and inviting humanity to view the cosmos through a broader lens. Loeb's perspective on 3I Atlas reflects a scientific philosophy that refuses to accept the universe as silent or indifferent. For him, every interstellar object is a potential messenger, not merely a random wanderer of rock and ice, but a carrier of meaning, a fragment of galactic narrative that might connect us to something greater. When Loeb speaks about 3I Atlas, he does not limit his vision to orbital mechanics or spectroscopy. He speaks of purpose, of possibility, of communication between the stars through the language of physics and motion. Loeb's thinking begins with an unflinching premise: we must not assume that what enters our solar system is merely natural. The universe, after all, has existed for nearly 14 billion years, long enough for civilizations to rise, fall, and scatter their artifacts across the galaxy. In his earlier work with the mysterious Oumuamua, Loeb proposed that such interstellar visitors might be technological relics, objects designed, launched, or abandoned by intelligent life. It was a hypothesis met with skepticism, but one that opened a profound dialogue in science. Should we not treat anomalies with open curiosity rather than rigid dismissal? When 3I Atlas appeared, moving differently from its predecessors, Loeb's scientific instinct once again leaned toward curiosity rather than complacency. According to Loeb, the fact that 3I Atlas appears to be staying in the solar system is a clue too important to ignore. Most interstellar objects enter at immense velocities, fly past the sun, and escape forever. But Atlas seems to have been captured, drawn into an orbit that may keep it bound for thousands or even millions of years. In Loeb's view, this raises questions that go beyond gravitational coincidence. Could an object be intentionally placed on such a trajectory? Could its path be a designed outcome rather than a random event? Such questions do not claim alien intent. They simply ask that we allow for the full spectrum of possibility in a universe vast enough to contain both natural beauty and artificial design. The heart of Loeb's hypothesis is a simple but transformative idea: that humanity's search for meaning in the cosmos must expand beyond radio signals and telescopes aimed at exoplanet. The universe may not communicate through electromagnetic words, but through material gestures, through the quiet arrival of objects that carry within them clues about their makers or their origins. An interstellar object could, in theory, serve as a vessel of knowledge, a message encoded not in language, but in structure, composition, or trajectory. Even if entirely natural, its arrival teaches us something about the conditions of other star systems, about how debris travels between them, and about the potential for interstellar exchange. But if, by chance, an object like Atlas ever showed characteristics that defied natural explanation, anomalous material properties, non-gravitational motion, or signs of engineered geometry, it could represent something far more profound. Loeb's philosophy is not rooted in fantasy. It is rooted in the discipline of empirical openness. He argues that the line between natural and artificial is one that must be tested, not assumed. To him, science is at its most powerful when it questions what seems obvious. The tendency of traditional astronomy, he believes, has been to explain anomalies away before exploring them deeply enough. This cautious conservatism, while protective against false claims, can sometimes blind us to discoveries waiting at the frontier of our understanding. When Loeb looks at 3I Atlas, he sees not a conclusion, but an invitation and opportunity to design instruments, missions, and methods capable of studying such objects in greater detail before they vanish, or in this case, as they remain. He often refers to 3I Atlas as a cosmic gift, a chance to observe an interstellar object up close without the urgency that accompanied Oumuamua's fleeting visit. Because Atlas appears to be staying, humanity has time to prepare, to study, and perhaps even to reach it with a probe. Loeb envisions missions that could intercept such captured interstellar bodies, analyze their composition directly, and send back data that could rewrite our understanding of galactic chemistry, and perhaps even interstellar communication. In his words, the universe might already be speaking to us, but we are not listening in the right way. 3 Atlas is indeed a galactic messenger. Its message may not be in symbols, but in physics, in its speed, in its stability, in the materials that compose it. Loeb encourages scientists to read such signals as one would read a book written in the alphabet of matter and motion. An object's density distribution, reflectivity, or energy absorption characteristics could be meaningful indicators of artificial origin. A fragment of metal alloy unknown in natural environments, or an isotopic ratio inconsistent with any known stellar process, would force a reevaluation of our cosmic assumptions. But even if Atlas proves entirely natural, Loeb argues, its capture is no less miraculous, a testament to the way gravity weaves together distant systems in silent communication. Loeb's critics sometimes accuse him of overreaching, of dressing imagination in the language of science. Yet he welcomes such skepticism, because it forces the community to define its boundaries more clearly. In truth, Loeb's approach revives an ancient human instinct, the drive to interpret the unknown not as chaos, but as potential meaning. When ancient civilizations looked at comets, they saw omens. When early astronomers mapped the stars, they sought order in their motion. Loeb's ideas, though wrapped in the mathematics of modern astrophysics, carry that same primal curiosity. He does not claim that 3I Atlas is a probe or a beacon. He simply insists that we do not rule it out. Part of what makes his perspective compelling is that it bridges the gap between scientific discipline and existential wonder. In Loeb's view, the universe is not a sterile laboratory, but a dynamic arena of interaction between stars, between civilizations, between moments of chance and intention. To believe that interstellar objects are merely random is to underestimate the creative complexity of cosmic evolution. He argues that intelligence itself may be a natural extension of cosmic processes, that the emergence of technology, like the formation of stars, may follow universal principles. If that is true, then the remnants of other civilizations may drift through space just as naturally as comets do. In that context, studying 3I Atlas is not just a matter of curiosity, but of participation in a grander cosmic dialogue. Loeb also frames this discussion within a deeply philosophical question. What if humanity itself is part of the same interstellar cycle? The heavy elements in our bodies were forged in ancient stars. The materials of our world once drifted as dust between suns. In time, our own creations may escape the solar system, becoming interstellar objects in another system's sky. To study Atlas, then, is to look at a mirror of what we might someday become. Travelers between the stars, silent and enduring, carrying the signatures of our existence into the endless night. The possible artificiality of 3I Atlas remains unproven, but the hypothesis carries weight, not because it asserts certainty, but because it expands perspective. Loeb reminds the scientific community that the extraordinary should not be dismissed merely because it is rare. Probability, after all, loses meaning when measured against the scale of the cosmos. In a galaxy with hundreds of billions of stars, even the most improbable event may occur countless times. Perhaps somewhere, long ago, a civilization launched probes across interstellar space, and some of them still drift indistinguishable at first glance from natural rocks. Perhaps 3I Atlas is one of them, or perhaps it is not. Either way, it demands our attention, His vision has inspired discussions within organizations such as the Galileo Project, which Loeb founded to systematically search for evidence of extraterrestrial technology near Earth and within the solar system. For the first time, instruments are being designed not merely to look outward at exoplanet, but inward at the small visitors passing through our cosmic neighborhood. The idea is to prepare for the next atlas, to have the capability to capture data before speculation fills the void. Loeb believes this proactive approach could transform the search for life from a passive listening exercise into an active exploration of the physical artifacts that may already be among us. In the quiet language of his scientific papers and public talks, Loeb often returns to a single theme: humility before the universe. To him, 3i Atlas is not just an object, it is a question, an invitation to humility, a reminder that the cosmos may still hold surprises that challenge even our most sophisticated models, whether natural or artificial, accidental or intentional. Atlas embodies a truth that Loeb has always emphasized, that discovery begins where certainty ends. It is a reminder that we are newcomers in a galaxy that has been exchanging matter and perhaps meaning for billions of years, and that sometimes, when the universe sends something our way, our task is not to dismiss it, but to listen. Discovery of 3i Atlas has done more than simply intrigue astronomers. It has shifted the trajectory of how humanity thinks about interstellar exploration itself. Before its arrival, interstellar studies largely belonged to the domain of theory, equations, simulations, and distant observations of exoplanet systems far beyond the reach of our instruments. The few interstellar visitors we had observed, like Oumuamua and Borisov, were fast-moving strangers, glimpsed briefly before they vanished into the night. But 3i Atlas changed that paradigm. It did not just pass through, it stayed. That single fact redefines the scope of possibility, both scientifically and philosophically, for the future of studying objects that come to us from beyond our sun's domain. To truly grasp what this means for science, one must understand the rarity of interstellar capture. The solar system is a dynamic dance of gravitational forces, a balanced, precise system where the planets, moons, and asteroids move under the sun's pull in predictable orbits. For something from another star to enter and remain within this gravitational system, its energy and velocity must align almost perfectly with the complex gravitational landscape of our planetary family. It's like catching a comet with bare hands as it streaks through the void. The fact that this may have happened naturally opens an entirely new chapter in cosmic research. It means that our solar system is not merely a closed environment. It is a participant in the grand exchange of matter that occurs throughout the galaxy. For scientists, 3i Atlas represents a once-in-a-lifetime opportunity to study an interstellar object without the urgency of time pressure. When Oumuamua was discovered in 2017, it was already on its way out, too fast and too faint to study in depth. Astronomers had only days to gather what data they could before it slipped beyond the reach of telescopes. The same was true for 2i Borisov, which streaked through the solar system with the classic brilliance of a comet, but escaped just as swiftly. 3i Atlas, however, lingers. It remains bound, moving slowly, offering scientists years, perhaps decades, to observe its motion, its spectrum, its interactions with solar radiation. That temporal advantage cannot be overstated. It is as though the universe has left a specimen in our cosmic laboratory, waiting for us to examine it at leisure. This opportunity has sparked conversations about the future of interstellar missions. For decades, humanity has dreamed of reaching the stars, of sending probes beyond the boundaries of the solar system. Projects like Voyager, Pioneer, and New Horizons have given us glimpses of that vastness, but always as outward journeys, one-way voyages into the dark. Now, for the first time, we are faced with the inverse, the possibility of studying a visitor that has come to us from the stars. The scientific community is already envisioning missions that could intercept 3i Atlas, similar in spirit to NASA's OSIRIS-REx mission that visited the asteroid Bennu. A probe could be launched to rendezvous with Atlas, study its surface, and perhaps even return samples to Earth. Such a mission would not only reveal the composition of another system's material, but could also demonstrate the technical feasibility of capturing and studying future interstellar arrivals. This idea has inspired new frameworks for space exploration, what some scientists call interstellar archaeology. Instead of waiting for clear signals from alien civilizations or distant exoplanet observations, researchers are beginning to see the objects that wander into our solar system as relics of galactic history. Every piece of matter that enters from beyond may carry traces of another system's chemistry, dynamics, and even its past collisions or planetary processes. In this sense, 3I Atlas is a messenger not of intent but of information, a tangible fragment of another solar system story, preserved in the vacuum of space and delivered into our reach. Avi Loeb has championed this approach, urging the scientific community to build the tools and infrastructure necessary to study interstellar objects in real time. He emphasizes that detection must be followed by swift action, not merely observing from afar, but moving toward the object with robotic missions capable of sampling and measuring on the spot. Loeb's Galileo project, for example, seeks to prepare Earth's technology for such encounters by developing telescopes, sensors, and algorithms capable of rapidly identifying and characterizing unidentified aerial and space phenomena. 3I Atlas, by staying within our solar system, provides the perfect proving ground for that philosophy. It gives us a test case, a chance to refine our ability to identify, track, and perhaps one day, engage with interstellar materials before they vanish again into the cosmic sea. One of the most important scientific lessons from 3I Atlas lies in the way it challenges our assumptions about interstellar material exchange. Until recently, the idea that material from other star systems could regularly enter and remain within ours seemed improbable. But now, astrophysicists are reconsidering the frequency and impact of such events. Simulations suggest that every solar system in the Milky Way may exchange debris over cosmic timescales. Small asteroids, cometary fragments, and dust grains that travel between stars, carrying with them information about their origins. If that is true, then the Milky Way is not a collection of isolated systems, but an interconnected ecosystem of matter. Over billions of years, fragments from countless worlds may have crossed paths, mixing and mingling the elemental signatures of alien suns. This has profound implications for the origins of life. If organic molecules or even prebiotic compounds can survive the journey between stars, then interstellar capture could be one of the mechanisms through which life's ingredients spread across the galaxy. The idea of panspermia, once considered fringe, gains new scientific footing when viewed through the lens of interstellar capture events like Atlas. If comets or asteroids from other systems occasionally become bound to ours, then it's plausible that the reverse has also happened, that fragments ejected from the early solar system have seeded distant worlds. In this sense, 3I Atlas becomes more than a scientific curiosity. It becomes part of a cosmic narrative of life's potential diffusion, a thread connecting the biology of Earth to the chemistry of other suns. The study of Atlas also brings technological challenges and opportunities. Future missions will require propulsion systems capable of reaching interstellar speeds, navigation that can adapt to uncertain trajectories, and instruments sensitive enough to study materials that may have compositions unlike anything found on Earth. The lessons learned from this object could shape the design of next-generation spacecraft, making interstellar interception a realistic goal rather than a distant dream. Researchers envision small, agile probes equipped with AI-driven navigation, capable of autonomously adjusting their course to meet such objects on short notice. These missions could mark the dawn of a new kind of exploration, not outward-bound, but inward-focused, examining the visitors that arrive uninvited yet laden with cosmic insight. Beyond the technological realm, 3I Atlas challenges humanity to rethink its place in the universe. For centuries, we have gazed outward, searching for meaning in distant stars, assuming that discovery lies somewhere beyond reach. But now, discovery has come to us. The cosmos has delivered something across light years of emptiness, placing it gently within our sun's gravitational cradle. Whether Atlas is a natural fragment or something more complex, its presence is a reminder that the universe is not indifferent. It is dynamic, interconnected, and alive with motion. The boundary between our solar system and the interstellar beyond is no longer fixed. It is porous, open to exchange, and full of surprise. This realization has philosophical weight. The more we study interstellar visitors, the more we begin to see ourselves as part of a galactic continuum rather than an isolated species on a solitary world. The future of interstellar studies, therefore, is not only about collecting data, but about cultivating perspective. Every object, like Atlas, invites us to confront the vastness of time and space, to recognize that our solar system is a node in an infinite web of gravitational and material relationships. The particles that make up our world, the iron in our blood, the carbon in our cells once drifted through that same web, forged in stars long dead. Carried across light years by forces we are only beginning to understand. As new generations of telescopes come online, the Vera C. Rubin Observatory, the James Webb Space Telescope, and others, we will likely discover many more interstellar visitors. Each will bring its own mysteries, its own chemistry, its own history. But Atlas will always be remembered as the one that stayed, the one that gave humanity time to look closely, to plan, to imagine. It represents the beginning of a new era in space science, an era where discovery is no longer limited to distant starlight, but extends to the very material drifting through our celestial backyard. The study of such objects will require collaboration across nations and disciplines, uniting astrophysicists, chemists, engineers, and philosophers under one shared goal: to understand what the universe sends our way. In many ways, 3I Atlas has already achieved something remarkable, has reignited humanity's curiosity about the unknown. It reminds us that science is not merely about explaining, but about wondering. It encourages us to prepare, to watch, and to listen for the quiet arrivals that may hold answers to questions we have yet to ask. And as we move deeper into the age of interstellar study, it teaches that perhaps the universe has always been reaching out to us, patiently, persistently, through fragments of stone and ice that cross the void and come to rest beneath our sun's light. As the final echoes of this journey settle into silence, we return to where it all began, under the same quiet stars that watch 3I Atlas glide into our solar system. It came as a stranger from another world, yet in its persistence, in its refusal to leave, it became part of our story. Through Avi Loeb's questions and the open-minded pursuit of discovery, we are reminded that science is not merely about what we know, but about what we dare to imagine. 3I Atlas challenges the boundary between ours and theirs, between the known and the infinite beyond. Its orbit, its presence, and its mystery reveal that the solar system is not a closed chapter in the universe's vast book, but an ever-expanding page, written by the movement of stars, the pull of gravity, and the curiosity of those who look upward and wonder. This small interstellar traveler, staying quietly within our celestial home, invites us to see connection where we once saw separation. It tells us that we are part of a living galaxy, bound by unseen forces and shared origins. And perhaps, in that realization, there is comfort that we are never truly alone in the dark, but surrounded by travelers, each carrying whispers of distant worlds and forgotten suns. As we drift into rest, let the thought of 3I Atlas linger, a symbol of cosmic continuity, of discovery still unfold, of a universe that continues to reach for us just as we reach for it.